Welcome back to the curriculum. This is Stage 6, Lesson 46, and we're going deep on IPsec. Over the next few minutes, we'll unpack what IPsec actually is as a suite of cooperating protocols, how ICAI negotiates the security, how ESP and AH protect the traffic, and where transport mode and tunnel mode each fit in. By the end, you'll have a clear mental model of the control plane and the data plane working together. So here's the roadmap for the next few minutes. We'll start by laying out the IPsec architecture itself, the cast of protocols that cooperate to make this thing work. Then we'll walk through IKE, both Phase 1 and Phase 2, to see exactly how a tunnel gets negotiated and brought up. From there, we'll compare ESP and AH to understand your encryption and integrity choices, and we'll finish on transport versus tunnel mode, when each one is the right tool for the job. So let's meet the cast. IPsec isn't a single protocol, it's a family, and the cleanest way to keep them straight is the control plane versus data plane split. IKE runs on UDP 500 or 4500 when NAT-T kicks in, and its job is purely negotiation, agreeing on algorithms, keys, and lifetimes. ESP, which is IP Protocol 50, is the workhorse that actually encrypts and authenticates your packets. AH, Protocol 51, gives you integrity without encryption, technically still around, but rarely deployed today. And tying it all together is the SA, the Security Association, a one-way agreement that lives as internal state on each peer, tracking every active tunnel. One quick note on the RFCs, ICAVs, defined in RFC 7296, superseded V1 back in 2014. If you're building something new, always prefer V2. Now, IKE itself runs in two distinct phases, and it's worth understanding why. Phase 1, EZECamp, exists purely to build a secure management tunnel between the peers. They authenticate each other, agree on AES 256, SOA 256, a Diffie-Hellman group, and a lifetime, and the result is a single bidirectional ASYNC KMP SA. Then, safely inside that encrypted channel, Phase 2 negotiates the parameters for the actual user data, the ESP protocol, the encryption suite, transport versus tunnel mode, and which subnets, the proxy IDs, are protected. And notice the output. Phase 2 produces two unidirectional IPsec SAs, one inbound, one outbound, which is exactly why SAs are always described as one way. Now, staying inside Phase 1 for a moment, Okevin actually offers two flavors, and the difference matters. Main mode takes 6 messages and keeps the peer identities encrypted, which is why it's the default for site-to-site tunnels between known static endpoints. Aggressive mode compresses that down to 3 messages. Faster, yes, but it exposes identity hashes in clear text, which makes it vulnerable to offline cracking. IKEV2 sidesteps the whole debate. One streamlined 4-message initial exchange, identities always encrypted. If you're building anything new, use IKEV2, full stop. With the control plane sorted, we shift down to the data plane, the protocols that actually carry your encrypted traffic. There are 2 choices here, ESP, Protocol 50, and AH, Protocol 51. The critical distinction is confidentiality. ESP encrypts the payload, AH does not. AH sends everything in clear text and only proves the packet wasn't tampered with. Both offer integrity, authentication, and anti-replay, but AH authenticates the entire IP header, which means the moment a NAT device rewrites that header, AH breaks. ESP lays nicely with NAT-T, so in the real world, ESP is the default everywhere. AH is legacy, useful only in the rare case you need full header authentication and you're guaranteed no NAT in the path. Once you've picked ESP, the next decision is how much of the packet you want to wrap. In transport mode, the original IP header stays visible and only the payload, TCP, UDP, and data gets encrypted. That's fine for direct host-to-host encryption where the endpoints are already routable. Tunnel mode goes further. It takes the entire original packet, encrypts it whole, and slaps a brand new outer IP header on the front with the gateway addresses. That's what makes site-to-site VPNs work. private IPs stay hidden, and the ISP only sees gateway-to-gateway traffic. In practice, tunnel mode is the default on every piece of VPN gear you'll touch. Transport mode is the rare exception. Now, the strength of that whole tunnel comes down to the Diffie-Hellman group you negotiate during IKE. The old MODP groups, 1, 2, and 5, are effectively broken or dangerously weak. You'll still find them in legacy configs, and that's exactly the security debt you want to pay down. Group 14 at 2048 bits is the bare minimum that's still acceptable, but the modern default is elliptic curve, Group 19 or 20. etcdhe, which gives you stronger keys with far less computational cost. If the peer supports curved 5E51 and 9 as Group 31, even better. It's fast, modern, and free of the historical baggage around NIST curves. Let's put all that theory into actual Cisco syntax. Step 1 defines the EK of 2 proposal. That's your Phase 1 crypto. AES 256 CBC for encryption, SHA 246 for integrity, and Group 19 for ETDHE, key exchange, exactly the modern choices we just discussed. Step 2 builds the keyring that ties a pre-shared key to the branch peer at 203.0 on 3.2. Step 3 is Phase 2, the ESP transform set in tunnel mode. That's what actually protects the data plane. And Step 4 binds it all to a tunnel interface via the IPsec profile, which is the cleaner, more modern alternative to legacy crypto maps. Now here's a real-world wrinkle that config alone won't solve. What happens when one of your peers sits behind NAT? IPsec breaks, and the reason is fundamental. ESP is IP Protocol 50, not TCP or UDP, so it has no ports for NAT to rewrite. Most NAT devices just drop it, and AH is even worse because it authenticates the IP header that NAT is about to change. The fix is NAT traversal. During IKE Phase 1, both peers detect NAT in the path, switch from UDP 500 to UDP 4500, and wrap every ESP packet inside a UDP 4500 header. Now NAT has a port to translate, ESP rides through cleanly, and you pay about 8 bytes of overhead per packet. The good news, it's all automatic today, negotiated during IKE with no manual configuration required. Now, even with all that theory in place, IPsec tunnels still fail in production, and they tend to fail in the same handful of ways. Top of the list, mismatched Phase 1 or Phase 2 parameters. If one side proposes AES 256 with SHA 256 and DH Group 19, and the other only offers AES 128 with SHA 1, there's no overlap, and the tunnel simply never forms. Right behind that, proxy ID mismatches. One side protects A24, the other O16, and Phase 2 collapses. Then PSK typos, which are brutal to debug because logs just say invalid hash. Copy-paste the key. Or better, move to certificates. MTU is another silent killer. IPsec adds around 70 bytes of overhead, so packets near 1500 fragment. Ping works, but HTTP hangs. Clamp MSS to around 1360 and you're fine. And finally, NAT in the path without NAT-T, which we just covered. Memorize this list. It'll save you hours. So let's pull the whole picture together. IPsec isn't one protocol. It's a suite. IKE on UDP 500 and 4500 runs the control plane. ESP as IP Protocol 50 carries the data, and AH is the relic you can safely ignore. Phase 1 authenticates the peers and builds the management tunnel. Phase 2 builds the actual data tunnel on top. Always pick ESP over AH, default to tunnel mode for VPNs, and standardize on IKE of 2 with AES 2FV6. HA 256, and DH Group 19 or higher. Do that, and NAT-T quietly handles the messy middle for you. Master the phases. You've mastered IPsec. And here's your one-page reference to keep next to you while you're configuring or troubleshooting. Notice how it's organized along the same mental model we've been building. The suite at the top, then the control plane and data plane protocols, then the 2 phases, and finally the mode choices that sit on top of them. If you can recall what each row means without looking at the right column, you genuinely understand IPsec, not just memorized it. And that closes out IPsec. Next up, in Lesson 47, we shift from the network layer to the application layer and dig into TLS and SSL, the handshake, certificates, and the public key infrastructure that makes the whole web of trust actually work. If this lesson clicked for you, head over to dargslan.com or the YouTube channel for the full series, and I'll see you in the next one.